Hello, everybody. I'm Souza from Universidade Federal Fluminense in Brazil, and I'm going to present a joint work with Sau from Montpellier. The topic of this talk is about hitting forbidden use subgraphs on bound treewidth graphs. So first I will present an introduction and some known results about the parameterized complexity of the problem. After that, I will present all results and our conclusion. So induced subgraphs is probably the most important graphic structure in the literature. Given a graph G and a set S of the vertices of G, the induced subgraph of G induced by S is the graph whose vertex set is S and the edge set consists of all edges of G that have both endpoints in S. There are many important types of induced subgraphs that include induced paths, induced cycles, cliques, and independent sets. Also, there are a lot of important families of graphs that can be described by list a set of forbidden induced subgraphs, such that cluster graphs, cographs, triangle-free graphs, pole-free graphs, split graphs, chordal graphs, and perfect graphs. In this talk, we are interested in a vertex deletion graph modification problem. This kind of problem have a graph G under Gk and a graph class C, and the goal is to determine the minimum number of vertices that we need to remove in order to obtain a graph in the class C. And in the decision problem, we must decide if there are a set of size at most k that we can remove in order to obtain a graph in the class C. And we know that this kind of problem is NP-complete if the graph class is a hereditary graph class and the property of being in that class is non-trivial. This is a result of Lewis and Yanakatz. And that is exactly the case of H-free graphs. The property of being H-free is non-trivial, and the class of H-free graphs is a hereditary graph class. And that the non-triviality happens for any H of size at least 2. Then the problem H-induced subgraph deletion is NP-complete for any subgraph, for any graph H of size at least 2. In particular, if H is isomorphic to K2, then we have the vertex cover problem. And if H is isomorphic to an independent set of size 2, then we have the dual of maximal clique. From the parameterized complexity point of view, taking K, the size of the solution as a parameter, we know that the problem can solve in FPT time using a bound search tree. Besides, we know that this is a particular, for a fixed H, this is a particular case of a hitting set. Then, by the sunflower hammer, we have that the problem has a polynomial. Also, we know that the property of being H-free can be expressed in monadic second order logic. Then the problem of find the minimum S such that G minus S is H-free can be solved in FPT time with respect to clique width and treewidth. The Cuselli theorem allows to prove that the problem is FPT, but the dependence of the treewidth of that algorithm can be very large. Then, in this talk, we are interested in solving H-free vertex deletion, parameterized by the treewidth, and we are trying to analyze the smallest possible function of the treewidth to solve that kind of problem. And this problem is a particular case of a family of problems that have been considered in the literature with respect to the computation about in graphs of bound treewidth. For example, H-minor deletion, H-topological deletion, and H-subgraph deletion have already been considered in the literature, However, a systematic study about H-induced subgraph deletion was missing, and one of the goals of this talk is to fix that gap. So first we start with a general dynamic programming that uses nice tree decomposition to solve H-induced subgraph deletion. So if you are interested in produce a dynamic programming to solve H-free vertex deletion in a bottom-up manner, we need to store many informations because we need to store any biases of the subgraph of H that we have at the moment, because when we introduce a new vertex, we need to recognize if this new vertex that have been introduced form a new copy of H or not. So, to save a few information, we just need to observe that a copy of H sometimes may appear inside the bag of the tree decomposition. And in that case, we don't need to store information about this copy because you can locally check in the bag if some copy of the forbidden subgraph will appear in that induced graph, induced bag. However, if you know that a copy of H does not occur inside the bag, then we know that when we introduce the last vertex of the bag, then at least one vertex of that bag has been forgotten. Then this implies that we don't need to store, to index the matrix with copies of size h minus 1, because copies, pieces of size h minus 1 will be important only to check the existence of a copy of size h inside the bag, and in that case we can perform a local checking. Then, this saves some few information that make it able to solve the problem into the treewidth to h minus 2 and not minus 1 that should be the most trivial. Now we start to consider some particular cases of H. The first one are the cliques. And if you are interested to KH induced subgraph deletion, then we must observe that any clique of a graph must appear inside a bag of the decomposition of the graph. Then we don't need to store additional information to try to check in the occurrence of the cliques. We just need to, for each bag, to guess the set of vertices that must be removed. And in that case, we know that that it's enough to solve the problem because all the cliques are inside the bag, so we can check if this guessing is variable or invisible for this kind of problem. So it's very easy to solve the problem in single exponential time. The problem becomes more interesting if we consider independent sets. Looking for an independent set, we have no guarantee that an independent set will appear inside a bag like the click case. And also for a subset of vertices inside the bag that is an independent set, since that we need to store information if they has a common non-neighbor or not. And if you're looking for this kind of subsets, this means that we need to store the same information like the general case, which will result in an algorithm in order of 2 to the 3 with to h minus 2. For example, it's not so easy to think about how to solve the problem for independence of size 4 without store information about pair of non-adjacent vectors that occur inside the bag. However, to solve that problem in single exponential time, you can use a different strategy that it's not based on a bottom-up dynamic programming. And to do that, we must think about independent set deletion, and the base case is independent set of size 2 deletion. This kind of problem is the dual of the maximal clique. This means that if you remove an optimal set of that problem, then the result graph is a clique. So we know that a clique is contained inside a bag. Then this implies that the result after the removal of an optimal solution, the remaining vertex is contained in just one bag. So we could ask if it's possible to generalize this kind of property to independence of size h. To do that, we need to think about chordal graphs that are free of independent sets of size h. And we will show that chordal graphs free of independent sets of size h has a clique cover of size at most h minus 1. So for h equal 2, we have that the problem is trivial because h minus graphs free of independent sets of size 2 are cliques, and the cliques are contained in a bag after the decomposition of the graph. So if you think now that the graph is chordal when free of an independent set of size h greater than 2, then we must remember that any chordal graph has a simplicial vertex. Then take a simplicial vertex, and we know that its neighborhood is a clique, and after the removal of that clique together with that vertex, we know that the result graph is also chordal because the property of being chordal is hereditary, and it also must be free of independent sets of size h minus 1 because the remaining vertex is in the non-neighborhood of the vertex v. So by induction, we know that the remaining vertex has clique cover of size h minus 2, then the graph has a clique cover of size h minus 1. Now, if you take a pre-decomposition of the graph G and the solution S to the independent set of size h deletion, we can construct the chordal graph that we obtain by edges between any pair of vertices that occur in the same bag. Then we obtain a chordal graph, and the pre-decomposition is also a pre-decomposition of that chordal graph. Sizing chordal is a hereditary problem, and the property of being free of independent sets of size h is close under edge completion. Then we obtain that the graph, the chordal graph G star minus the subset, the set of vectors S, is also cordal and free of independent sets of size h. Then, by the previous lemma, we have that this graph has a clique curve of size at most h minus 1. And we also know that the triple decomposition T is also triple decomposition of G and G star. And the vertices of G star minus S are covered by H minus 1 bags. And the subset of vertices are the same in G star and G. So this also implies that there are at most H minus 1 bags of G that cover all vertices of VG minus S. Then we have that there are at most H minus 1 bags that cover all the remaining vertices of the removal of our optimal solution for the problem of hitting dependent sets. Then this is the main tool to solve the problem in single exponential time, because we just need to guess the subsets of bags of, that contain remaining vertices. So we just need to solve a minimal set of bags that contain the set of vertices that remains after the removal of our optimal solution. So a naive approach, it's sufficient to solve the problem in single exponential time, but the dependence of n is not linear. But in a bottom-up manner, we are able to solve that in single exponential time and with linearity in the number of vertices. Now we start to talk about the lower bounds for solving H-induced subgraph reduction. Size every clique contained in a bag, then we know that the problem of KH in the subgraph deletion can be solved in single exponential time. Now we start to talk about a clique minus one edge. So this means that this forbidden subgraph has exactly one non-edge. And we are asking about the complexity of hitting this kind of problem, this kind of induced subgraph. And we show that for that kind of subgraphs, we cannot do better than 2 to the 3 with 2 h minus 2 unless eth fails. To proceed that, we present a reduction from research. And for that, for each variable of the formula, we create a get like that, where we have 4 important vertices that represent literals of the variable. And for each pair, positive and negative, we have a copy of the forbidden subgraph. In this kind of get, we know that any optimal solution must remove 2 vertices of the bag, and it must be 2 vertices of the same time, or corresponding to positive or negative literals. And we apply the same for the clauses, where we create a gadget with 3 important vertices, and each one of these vertices represent a literal of the clause. And in this kind of gadget, we know that we must to remove at least 2 vertices, and a minimal solution will be use exactly 2 vertices that correspond to literals. Then we have the variable gadget and the clause gadget, and we need to connect them in order to preserve bound treewidth. So we will use gadget n, that we need to describe how we constructed that get. So first we need to think about the smallest possible integer such that as to the size h minus 2 is at least 3n. Note that this set as is not so big. So take this integer as, we can create a complete multipartite graph with h minus 2 paths, and each path has as vertices. Then we have the three main kind of vertices that we need. And also we just need to describe how these vertices of the variable and the closed vertices are connected, use M as an auxiliary gadget. So to do that, for each pair, close and literal, we create a function that maps integers in the interval of 1 and 8 to integers in the interval of 1 and s. And we do that, we create functions in a such way that for any pair close literal, we map a distinctive function. And this is possible because the integer s is in a such way that s to h minus 2 is at least 3n. And we know that for each clause we have at most 3 literals. Then we can map appropriately the pairs that have the same function. And then we know that there is, between the corresponding pairs, we have a forbidden subgraph. Then this implies that we must, for each clause, to remove 2 to each get variable get, we must to remove 2 vertices in a such way that we does not have forbidden subgraphs between, and this happens if and only if the formula was satisfiable. Then with that, we prove that assuming each 8, we cannot solve this kind of problem better than 2 to the treewidth to h minus 2. This implies, for example, that our general algorithm, embora very simple, is very simple, but in many times can be tight. And as a corollary, we know that diamond-induced subgraph deletion cannot be solved better than 2 to the treewidth 2 squared. We also extended this framework of reduction to other kind of problems. For example, KH plus an independent set of size 2 cannot be solved better than 2 to the treewidth to 8. And taking KHH, the complete bipartite, we cannot hitting this kind of subgraphs better than 2 to the treewidth to 8. We also, as corollary of the last case, that C4 induced deletion and C4 subgraph deletion cannot be solved in time 2 to the treewidth 2 square. Unless each fails, and that close of the question of the NFCS 2011. We also consider the colorful version of the problem, and we show that for connect components of H vertices that are not click, we also cannot do better than 2 to the treewidth to H minus 2. And it's that. Thank you.